Hello, everyone. Welcome to ITS 365, Machine Learning Fundamentals. So today is, as you know, we're currently on week 3. This is week 3. And today is lab day. So we are going to cover several things today. On the agenda, I have going over the first homework assignment. We're going to kind of discuss that. Then after that, I'm going to introduce you to a tool called, a library in Python called Numpy. So we're going to go over Numpy just a little bit. And then after that, the KNN algorithm, which should be pretty straightforward. So the reason why we're going to do Numpy is if you saw on Monday that I went over the Euclidean distance code, and I showed you how to do that with for loops, right? And that's great and everything, but I said it's not very practical sometimes because it's not very fast for big data. And so Numpy, on the other hand, is a way of representing data as matrices and vectors in a very simple way. And you can very much perform simple operations. And so although it derives itself from, an area of mathematics called linear algebra, we do not need to know everything about linear algebra to do the work that we need to do, right? We really just need to know a few operations, and it's like algebra, right? So you just in a slightly different sense, and so we can easily pick it up. So today I'm going to do that, and then that way we'll have both tools. We'll have, just doing code from scratch, the traditional way, but also you'll have a new tool to do code in this approach, right? The linear algebra approach via Numpy. And that way you'll be able to understand code that you see online, and you'll be able to write better, more efficient code. So my goal is that the KNN algorithm, we're going to try to implement as much of it as possible in this approach, Numpy. But that's why I'm going to give you a little bit of some examples, just kind of illustrate how it works. And then after that, I think you should be in pretty good shape. So that's the plan. We don't have Scholar yet set up. I know it's there, but I think Mitch was helping me to set up some of the environments. So hopefully by next week we'll have it. So today I think we can just use Anaconda. Hopefully you have that installed. Are there any questions before I begin? All right, doesn't sound like there's any questions. So let me share. Should have shared this. I always forget to share. Okay, so you should be seeing Brightspace. So as you can see in the pipeline, in the course modules, I just want to go over this today, kind of look at the problems, and then get your opinions so you guys can participate. And then KNN here, I will be adding one link certainly for some Numpy examples that I have on my GitHub, so that you guys can follow along or actually work through them on your own. And then we'll wrap up the lab today by working on KNN. I'm not going to fully solve it, and instead it's going to be a homework. So I think with what I'm going to give you today, you should be able to complete it in 1 week. Therefore, I will be assigning the KNN homework, KNN algorithm, to be due 1 week from today. So you can see here, homework, KNN. And then this will be due, today's the 27th, I guess, so on the 3rd of February, this will be due. But, we're going to get a lot of it done today. I would imagine. So that should be, no, I got that wrong. February. Huh. Why does it keep? This keeps doing. Do you guys see how what it's doing? Oh, okay. I think I get it. I get it. There we go. All right. So February 6th. All right. So implement the KNN algorithm as discussed in class. Right. Create some data. Train, test, and evaluate your model. Show your accuracy scores. Okay, so we'll talk about all of this, of course, but that pretty much should do it. Is this clear enough, guys, for as far as the homework?
Yeah.
All right, so today, as I said, I want to definitely go over the previous homework just quickly. We don't have to spend too much time on it. And then we'll come back to Numpy and just get into Numpy a little bit. Of all the libraries that are out there, besides, like the pure machine learning ones like sklearn, TensorFlow, and Python, the other three that are extremely important would be Numpy, Pandas, and Matplotlib. Okay, so Numpy certainly is, like it's, the expression, right? It does all the heavy lifting. So you really, if you understand how Numpy does things, then you sort of understand how TensorFlow does things, because TensorFlow just really tried to mimic Numpy. So we'll do some examples of it. Not too many complex ones, but the very simple ones for sure. However, in the link that I will provide, I strongly suggest it won't be homework, but I strongly suggest go through all those examples, implement them in your own computer, and you should be able to understand it. I do have a chapter in my book about that, so I may just share that chapter with you guys if you have too many questions. But otherwise, I think you can just implement the code and it should work. All right, so let's go ahead here in the machine learning pipeline and feature engineering. So this was the homework initially, right? And I just want to go over it a little bit to make sure everyone got this right, as I think it's pretty important. So I'm going to ask you guys to participate, maybe one student per problem, if you don't mind. So for the following 5 classification problems, identify and or define the following. What is the X matrix? What is the Y vector? What are the samples? What are the classes? Define a set of features. Define the dimensions of X and Y and indicate what they mean. And so let's start with the first one. So the first one is a classification model for a network intrusion detection system. So I'm going to switch over to the whiteboard. So who would like to kind of describe what they did?
I can go first because I kind of had a question.
Go ahead. Yeah.
So when you said like X vector, I'm pulling up my homework. When you said X matrix, I wasn't quite sure if you wanted us just to draw it and then turn in the drawing, or you wanted us to like just do like a list with the results in each of those.
I wasn't asking for code, no. And this
well, not code, but like just so like how I did it, I put like the Y vector and then I listed what will be in the Y vector.
Yeah, that's fine.
And I don't know if you can really list what's in the X matrix, because the matrix is just this.
You mean the values in there, right?
Yeah, because like because that will be the samples and features.
No, remember that the values would always be between 0 and 1 or -1 and 1, because they should be scaled anyway, right?
Okay.
So the values would always be, let's say, from a number from between 0 and 1 for all of them, because they're all scale.
Okay.
But the meaning of the features, though, is important, right? Make
Okay.
sense?
Yeah, no, that makes sense. So I can let you know what I did then.
Yeah. So what is then, what is it?
So I guess we could start with the samples, which would be on the left of the X, right?
Okay.
So for the samples, I put each of those, each sample would be a packet that was viewed by the
Yeah,
IDS.
packet, that makes sense.
And then for the features, which would be the top of the X, I put like the things inside of a packet, which would be like time to live, protocol number, source IP address, destination IP address, and like flags.
Right. So the flags would be zeros and ones, and then right. So let's say it's a SYN packet, right? So it's
Yeah,
either a 0 or a 1.
correct,
And then the TTL, that can be a number, right? You know,
correct.
4, 5, whatever. Good, good. IP address. IP addresses can be converted to numbers. They can, so I guess, but IP addresses fall into that category that this IP address is not necessarily, because it's lower than the other IP address, doesn't necessarily mean that it's meaningful, right? That one is lower than the other.
I mean, but when it looked at it, when the algorithm looks at it, wouldn't it just say like how many times this IP address occurs?
But in the packet, it will only occur one time.
Well, yeah, I was just thinking like in comparison between like 7 different packets. Like if one IP address happens 3 times, then it just assigns that IP address to be, say, for example, more of a malicious IP source, if
Right,
that
right.
makes sense.
But that requires some code to
Okay.
create that feature. You know what I
Oh,
mean? I
okay.
get what you're saying. There's some kind of, you have like a running total of IPs. I've seen this IP. I'm going to mark it as significant. I get what you're saying.
Correct. Okay.
So what you're saying is you're going to engineer a feature called like significance.
Well, no, I was just saying like wouldn't the algorithm itself de define if that IP address was a significant one? So if they kept getting a lot of, let's just say
Well,
we kept getting a lot of
what
IP
what
packets.
algorithm? I mean, your
Well,
algorithm.
I'm just saying like if we actually,
You have to write the algorithm, yeah.
correct.
So the feature engineering is all you. There is no magical, thing that does that. But I get what you're saying. You're defining significance of IP, but you need to write this code so that
Correct.
whenever you get a packet, you assign some kind of numbers here based on
Correct.
that logic of what you were saying. This one might be more suspicious or something. Make sense?
Yeah. Yeah.
Okay. What are your labels?
My labels would be true positive, true negative, false positive, false negative.
Okay. So really, though, that's something that will be captured in the confusion matrix, right? So really, all you have to define here is the target. Are you trying to find if it's a good packet or a bad packet, for instance? Remember that
Correct.
we'll talk about those true positives and false positives next week when we talk about performance metrics.
Well, I was just saying because it's an IDS, that's how you label packet,
Right,
right?
but you have to, a true positive has a meaning, right? So it's not a specific
Correct.
meaning. That it means that out of the ones that should be correct, these many were correct, these many were not correct. So we'll
Well,
talk.
yeah, I get what you're saying, but I wasn't referring in that sense. I was just referring to the sense that an IDS would say that it's either a malicious or
Yeah,
non-malicious.
I would just go with like that, malicious,
Okay.
not malicious. The problem when you say something like true positive is that you're taking away meaning that's already in one of the performance metrics.
No, I get what you're saying.
Yeah. So we'll see that again in the performance metrics where that should hopefully become a little bit clearer. Okay, good. What were your N and M? What were the sizes?
So like I put like 5 total features, so the N would be
So
like
five.
5.
Okay.
And then like the N, I mean, I didn't really know how, and this goes for all of them. I mean, because I just said samples would be a sample would be a single packet, so it depends
Right.
on
You'll
how
have a lot of.
many.
mean, if one thing that we know about networks is they have a lot of packets, right? So,
Yeah. So like something that's kind of something I didn't really understand with the homework either. Was like I was kind of rewatching your video and you said that so n is equal to like you have the same amount of x's as the same amount of y's, right?
you have the same, you mean the rows, right?
Yeah.
Yeah, so for this sample, you need a class. For this sample, you need a class, and for,
Right.
so
Because
dot, dot.
every single because every single input has an output, right?
Every single sample, right? So this is a feature vector, which is the representation of one packet. And that packet you scan, you looked at it, and it was a good packet. So then it gets a, good. But then you look at this packet over here, you represent it, as Josh said, as 5 features, what is the TTL, whatever. And then that has a label here. But that, Josh, when he did the analysis, said that, oh, that's malware. So he gave it an M label.
Mm-hmm.
You understand? So every sample, if you have n equal 100,000, here it's also 100,000, and they need to be aligned perfectly. Do you understand?
Yeah.
Does that answer your question?
Yeah, I just like what was kind of tripping me up, which I figured out, but I just thought that I thought that the Y's needed to all be unique for some reason when I was doing the homework, and
These Y's, these values,
yeah,
these values are the classes. So
right,
usually you don't want to have more than, say, like 10 classes. And
yeah,
the more common thing is like 2, 3, 4. So in the example of the IDS, goodware, malware, it makes sense, or intrusion, not intrusion, something like that.
right,
So every sample, this is real data, right? So if you grab this packet, you need to know what the actual data was for it, because your algorithm will learn to correlate this exact thing. It'll learn that whenever it sees these values, they correlate usually more with good than with bad.
mm-hmm.
You see that? All right, any other questions, guys? All right, so it sounds like it makes sense. So let's take a look at the second one, and let's just, have another student maybe go over it. So the second one says, number 2, a speech-based classification model for a telephone menu. So we're all familiar with this, right? So e.g. for English, press 1, for Spanish, press 2, and so on. So a speech, so imagine on the phone, how would you build this classifier? So again, the same thing. Let's go to a new slide, and we're going to say speech. So who can just give it a try? The same thing, X, Y, and M, and 1. All right. So who wants to go first?
Well, I basically had no clue how to do this, but I'll give it a go.
Mm-hmm.
For my features, I did pitch, frequency, and loudness.
Okay, good. So you would get the speech signal, right? So an audio signal in the time domain, they look like that, right? And then there's a lot of code. There's librosa in Python. There's something called Prat. There's a lot of codes in code. You just basically take the .wav file, and then you run the code, and then exactly what you just said. It gives you the pitch. What else did you say?
Frequency and the loudness.
Frequency, loudness. Exactly. Very good. Exactly, because you're analyzing the audio, right? The actual speech audio signal. We're all familiar, I think, with WAV files. So good, excellent. So you extract those, you get those values, and they're going to be, numbers, real valued numbers. Okay. So 3. So this would have been 3 for you.
Yes.
Okay. So 3 features, right? And then what else did you define?
I just put a random sample size of like 10,000.
Okay, 10,000. So that means this one is also 10,000, right? And then what were your labels?
My labels were clear and unclear. I was really not sure what to do for that.
Yeah, that's fine. That's fine. So you're basically just saying, yeah, clear, not clear. You know what? Another one could have been speaking, not speaking, right? So like the pause that people have, you say something, pause, say something again, right? So that's perfectly fine.
See, I have a question. So
I-
for my labels, I put the actual like languages like English, Spanish, French.
Yeah,
Okay.
that's what I did too. I put
That's
like
fine.
the answers.
So,
Okay.
so what you just wanted to say English, Spanish, English, Spanish. Exactly. So you basically train the model, right? So the way that it works is you get a person, they speak Spanish, you label it as a 1. Then you get another person, they speak English, guess what? You label it as a 0. That's all you have to do. You don't have to do anything more complex than that. You're going to do this 10,000 times. Usually you want your data to be balanced, which basically means as much as possible, which is hard, sometimes very difficult to do. You want 5,000 English, 5,000 Spanish. All you have to do is, speak into the microphone in English, speak into the microphone in Spanish. Get all of those segments. You can define also here, one important thing about the sample, just like we did with the previous one with IDS, is define what the sample is. So we know it's an audio signal, but what else do we need to define about it? The length of the signal. I would recommend that they should all be the same size. So for instance, I don't know, 1 second. You guys understand that? Or
Yeah.
10 seconds. Does that make sense?
Yeah, it does.
Defining the sample is also critical. So in the previous one, a packet, we all, you guys are IT students, you understand that very well. Here, it's audio, so it's a wave file that lasts, let's say, 10 seconds. That's your sample. And that's fine. That's exactly what it is. You could have also done like 5 classes where you just define the following. You say to people, okay, it's not going to be about English and Spanish. It's going to be about yes, no, maybe, or yes, no, operator, right? So people say yes, yes. A lot of people say yes, a lot of people say no, and a lot of people say operator. And then basically that's all the classifier will understand. So so they'll use that particular function when they say, would you like to take the survey? And so you say no, and so the classifier learns it. Does that make sense, guys? So it doesn't have to be binary. It could also be, 3 classes or 5 classes, but just don't have too many classes. Is this clear?
Yeah.
Yeah. And then the values here, whatever the values would be, of course, remember, they need to be scaled. And we'll get to that. I'll show you guys some functions for that. But basically, I've already explained this. You pretty much you always want your data scaled.
What do you mean by scaled?
What do I mean by scaled? So in one of the videos, we talked about scaling our data. So what that means is, let's say that I have, income, right? So income is, you say you make, 200,000 a year, and then, but then you also have, politics, right? Politics, and then that's just really 0 or 1. Man, that's pretty small number. And then you have over here, you have square feet of your house, whatever. And I'm just gonna make up some number, 2,000. So remember that these are features F1, F2, F3, right? So if you think of these as axes in a vector space, you have one. Actually, you have 1, which will be from 0 to 200,000. Do you see that? That's, or actually 300,000, right? Maybe, because you might have people that earn more than that. But then what about this axis? This axis really just goes to 2,000. Do you see that? And the third one is even smaller from just 0 to 1. So the problem with this is, if you remember the plotting, right? The difference between these, right? You know, if you look at this range, it's pretty big. Look at how big it is. But if I look at the difference here between zeros and x's on this axis, it's only that. Do you see that? And so this distance, it's a lot shorter than this distance. Make sense? And that's a bad thing in a vector space, because this one, you know, this axis here will dominate completely. This one, basically the little one here, will be completely dominated. So what you want to do is you want
like them to be the same size.
Yes, them to be the same size. So you want actually something that's like that. Do you see that?
Yeah, okay.
You can do that by scaling, just by going from 0 to 1, 0 to 1, and we can always say, okay, so if we're going to define 0 to 300,000, right? Well, if it's 200,000, it falls around there, right? So we can
It'd be like 0.6.
Yeah, exactly, 0.6. Perfect.
6.
Like,
or
got
something.
it?
Yeah.
Seems like you got it.
Yeah, okay. So
That's
it's-
what
you want
should
them to be
always do
scaled.
this. Go ahead. Sorry.
You want them to be scaled, like as a ratio.
I don't want
essentially.
them. I mean, they should always be scaled.
Yeah.
Because hopefully you can see that otherwise, you know, this axis will totally dominate. You see that?
Yeah.
It'll always say, no, the difference here. Remember that it's all machine learning is doing is on every axis is looking at the spread, the difference. That, you know, that's a oversimplification, but intuitively though, you can think of it that way.
Yeah, no, it's starting to make sense now. I was really confused last like lecture when you were explaining the whole like the distance between the points on like multiple dimensions, but now it's starting to make sense. So like
Starting to make sense. All right. Yeah.
Yeah.
Just watch the videos in sequence, I think, and it should make sense. Any other questions? So it's clear, right? So scaling is clear. Guys?
yeah.
Yeah.
Makes
Okay.
sense to me.
Yeah, and we can come back to it. I mean, it's an important thing. At the end of the day, it'll be one of the little boxes in your pipeline. So you have your data, scale it, you know, get your data. And we'll introduce that. Actually, with Numpy, we'll probably introduce that too. But yeah, that's the idea. All right. So if there are no other questions, let's move on to the third problem, which is, let's look it up. So the third problem is a classification model for movie recommendations. Oh, this is a great one. And keep in mind, we're gonna do recommender systems in about 2-3 weeks. We're gonna get to recommender systems, which are a specific technique for that. But right now, I just want you to think about it, as I wrote over here, from the point of view of a supervised learning algorithm. So a classification model for movie recommendations, such as Netflix. As you guys know, Netflix recommends movies to you. All right, so let's just write Netflix here. So who would like to tackle this one?
I'll take a shot at this one.
Sure. Go ahead.
So the features would be like time spent watching a certain movie, like for a user.
Okay.
Um,
Average time, right? Average time for that movie or something.
yeah. Well,
Let's
why
start,
average?
Actually, let's start. What are your samples then? What are your samples?
A particular user's man, I don't have my homework on me right now. I'm at work right now, so I can't pull it up.
Mm-hmm. But just try. What do you think? So you have to define the sample, right? That's usually where we should start, actually. So what are you trying to achieve here? You're trying to recommend a movie.
Yeah, so It would be a user's viewing history.
Okay, users viewing history. Okay.
Um, the and then let's say n would be um like 10,000 users or something, right?
Okay, 10,000 users.
Uh, the features could be like previous like like one previous, so one time it would be the like or like maybe it could be a percentage of like the like completion of the previous movie that they watched, and
Okay.
then it would be like also the genre associated with that,
Okay,
and then you could
genre.
have that for like the past like 5 things that they watched.
Okay. So genre, and that could be several. What are the labels then? What are you trying to predict?
So then the labels would be like horror, comedy,
So genre as well. Okay, so horror.
because that would be the output, right? That would be the thing that they would be predicting.
Yeah, what type of movie to recommend, right?
Yeah.
Okay. All right. Yeah. So your labels are. I mean, it's fine, right? So I'm not saying it's totally fine. So horror, comedy, and then you have users. So you've defined these to be users, and then the features would be, you have a user. What should we recommend? Horror, comedy, and then the features would be, well, if they watch a lot of TV, right? That's kind of what you're saying here with time.
If they spent, like, for example, like, because I mean, if a user clicks on a like let's say a comedy, and they
Yes.
watch only about like 5% or 10% of the movie, and they click out, um probably that user doesn't like comedies, right?
Sure.
um
Oh, I see what you're saying. So you're saying time spent watching comedies, and then
yeah,
you'll have time spent watching sci-fi.
right, like,
I
yeah,
see.
so that's kind of, yeah, that's what I put in my homework. I think I had like different, like,
Yeah.
time spent for comedy, then or time spent watching uh like a comedy, and then time spent watching like each one of the genres, and then
Right.
those would also be in the Y
So for
vector.
instance, if these are point eight, but for user 2, point 2, point 2, maybe, and I'm generalizing a lot here, but if they watch a lot of comedy and sci-fi, maybe they won't like romance. But if they watch very little comedy and very little sci-fi, maybe they would like romance, right? Something like that.
Yeah.
Yeah, and yeah, that sounds about right. So that's good. That's good. So you have some features. Did you set a number for these? For how many features?
I mean, you would need as many genres as you'd be trying to recommend.
There could be a lot, right? So at least 100, probably 1,000 somewhere around. Okay. What about this end? What is this value?
It'd be also 10,000.
Okay, very good. And then how many labels would you set?
Again, I mean, it's just kind of like how many genres you
Just
want to.
here, this is an important question though. Just give me a number. Just
I mean, like you said, probably less than 10. So.
okay, good. All right, yeah. So don't have.
I mean, there are a lot of genres, and it's not something that has to be too very particular. So maybe 10 is a good number.
Okay, perfect. So I think that's all of it. Yeah, good. So the other thing is make sure, as I said, balance, right? As much as possible. Now this is hard to do, but so what I mean with, okay, so balance here, we have, let's say 5, let's say we have 5 classes. So if we have 5 classes, balance, what does balance mean if we have 5 classes with regards to the 10,000 samples? Balance would mean that we have 2,000 of each. Okay? That's balance. Again, it's not going to be perfect. One will be 1,500, one will be 2,500. That's still Balanced. Unbalanced would be, this one is 8,000. This one is, you know, oh yeah, 8,000. And then the other ones are small numbers, like, you know, this one's 100. And then the other ones make up the difference. This is an imbalanced data set. Do you guys see that?
Yeah.
Machine learning has a problem with that. Okay. All right, very good. I like this problem because when we try to do it in supervised learning, the Netflix problem, we actually realized one thing, that a supervised learning algorithm is not great for the Netflix problem. You see that, or this type of approach. It's not the greatest because we have the problem of so many. You know, you really want more labels here, right? Wouldn't you? I mean, that's what you wanted. That doesn't work really well. That's why we are going to do recommender systems, which are perfect for, you know, not just for Netflix, but any business, right? Where you know, supermarket, everything, anywhere where you want to recommend things to increase your sales. It's a recommender system. This is going to be based on singular value decomposition. That's the technique, and we will explore that in about 2-3 weeks. But I like to do this problem here to kind of actually contrast that, you know, you don't always need to hit, if supervised learning is a hammer, sometimes you need a different tool, a drill or something. Okay? Questions? All right, seems like there's no questions, so let's look at the next one. I just think this is pretty important, actually. We'll have time for the other stuff. All right, number 4 would be a classification model for weather monitoring. All right, so weather monitoring. So who would like to talk about this?
Sure, why not?
Okay.
For features, I did wind speed.
So let's start with, what are you trying to monitor exactly? What are you trying to
I'm trying to have it predict the I guess take a weather at a given time and then try to determine if it was snowy, rainy, cloudy, sunny.
Okay, so 4 labels then, it sounds. 4 classes. It wants to predict if it's snow, rain, cloudy, and sunny. Okay, that's good. That's 4 classes, 4 labels. Good. All right, so now what is a sample? What is your sample? How did you define your sample?
Well, for that I did like day 1, day 2, day 3.
Okay, so during a day, that's good. So you say on Wednesday, I'm going to go in and I'm going to take some measurements. And then I'm going to say overall that, okay, that's perfect. So one day of measurements. Okay, so what are the features now?
I have wind speed,
Okay.
precipitation over time, temperature.
Okay.
Cloud
So
coverage.
for these, you would take like an average, right? Maybe you would measure the temperature every hour, and then you write them down in a little notebook, and then you average them, correct?
Yeah.
Okay, perfect. That's and you do the same for all the other ones. Wind speed, precipitation. Good. How many features do you think did you come up with?
I came up with 6.
Okay, 6. And then how many samples would you say you would have over? Days, right? You have to do this over days. So
yeah, I just put a random number of 20,000, but I put 20,000, but
okay, think about, so I only say this because it's important. 20,000 divided by 365.
yeah,
How many years is that?
quite a few.
Yeah, quite a few, right? So what do you need? You need to maybe hire people and send them out throughout the country or something but that's then very expensive.
Yeah.
You see that? And so that's just the only thing to consider, right? So maybe for this one, let's say over 2 years, or if you hire people, right, shorter period, but about 1,000 samples. But you know, makes sense. Perfect. Okay, and this n, of course, would be also 1,000 because it matches. This one is 1, remember, not m. All right, good. Any questions about this one? And then remember, the values would still be scaled, right? So temperature, for instance, so Jacob, right? Temperature would be what? Fahrenheit, you know, from, let's say, 0 to 100, right? But wind speed, I don't know what it goes to, 400 miles an hour or something. But precipitation.
That'd be kind of crazy.
What?
400 miles an hour?
That's too much? What is a hurricane, 150?
Oh, no. Oh, true.
I don't
know.
He was just talking like an average day if there was 400 miles an hour wind.
Oh, yeah. And then the other, that's true. That would be that's probably Jupiter or something. And then here, precipitation, how does that measure? Is it measure in I guess?
Probably in inches, yeah.
Inches. So I'm trying to look, let's say it's measured in gallons though, and you're measuring a pool or something. So that would be a much larger thing, right? Or even droplets of water. I don't know. Something, the scales would be different. You see that?
Yeah.
That's my point with the features. So you have to scale it to be between 0 and 1. Make sense?
Yeah.
That makes sense.
Okay. All right. And the last one then. Let's this one. The last one says a classification model for cancer diagnosis using 3D image scans. Okay, so this might be a little bit more harder. So let's think about that one. All right, so cancer scans, 3D scans. Okay, so again, we need to think about that. So who would like to try this one?
I can try this one, but honestly, this one was the features for this one. I have zero idea about.
Go ahead.
So I can start with the samples. Each sample, I would say, would be a singular patient.
Okay.
And then for the Y vector, like the results for each patient, you're either viewing if they have cancer or they do not have cancer.
Right. So it's a 0 and 1.
Yeah.
Detected or not detected. Okay.
And the features for me were like the hardest part because I have no idea about this type of information. So I just put like if there's a growth or is there like an increase in density, or I don't even know X, Y, and Z as in like the plots of the scan.
Well, what it is a 3D scan. So it's an image, right?
Correct.
It's an image. And you don't even, let's say, I don't know, there's some tissue there. I'm just drawing. That's some tissue. Well, this is a 2D image. What they do with the 3D scan is it's not a picture, but it's something like, not sonar, but one of those machines that they have for scanning.
MRI.
LiDAR or, something based on LiDAR that can actually measure like a 3D object, right? So if you have a 3D object, right, it can actually measure, the projection of it. And so they'll just develop a whole bunch of images. That's why it's, you can think of it that way. Do you see that?
Yeah.
That's basically what that means.
No, I get that. I just don't know what you would be.
Yeah. So then,
for
what the features would actually be, let's say now, just to simplify it, let's say that a 3D scan is like 50 by 50 grids, right? So there's 5 of them and they're 50 by 50, and they basically each one looks like an image. It's basically like a picture, right, of depth of the object at that layer. So they're really pictures. You see that? That's my point. And if they are pictures, they can be treated in its simplest form. If they're 5, just kind of like concatenate them like this.
So like shrinkify them.
Yeah, shrink. Yeah, make them into like a long picture now, for instance, right? That's just super simplified version of it. And then once it becomes, so this becomes a picture that's long like this. And so now what can you do? Take every pixel as a feature.
But so like, say for example, you're doing the scan and you're just like scanning, I don't know, let's say bone or something, right? Like, I mean, I guess you obviously you can have cancer in your bones, but I mean, you just look, so each pixel you're just determining per pixel if the pixel itself is a cancerous pixel.
Nope. You don't do any of that.
Well, I mean, that's what this would be doing.
But the algorithm does it for you. You just provide the data. That's what I want you guys to understand is, here's the thing. You're in machine learning, you don't have to teach the AI to find the cancer. And that's actually the main definition of it, that in fact, you let the AI figure it out. Do you know what I'm saying?
Yeah, I understand. It's just, I don't know, medical,
I
I'm
get
just
what you want to
not.
do, Josh. What you
Yeah.
want to do is this. You want to have it, let's say an image, right? I made that 3D image into just one big 2D image. You want to have your own code. Josh's.
No, I don't, not for this. No, because no, for this, I'm saying I just really don't understand like medical
But
stuff.
I'm just
So
saying.
yeah,
No, that's fine.
Yeah.
So this is the image of tissues and everything, right? So I don't know, something like that. You're saying I'm going to create my own code that I look at these and I say in this segment that probably has cancer, which basically means you define these features yourself.
yeah.
And then that becomes X. You see that? This is what you're trying, where you're confused. What
Yeah,
I'm
actually,
saying,
that makes sense. Yeah.
what I'm saying is just feed this into the algorithm. And that's it, X. But remember that because you're also providing Y, the algorithm will learn to correlate images that have cancer, right, to features in the image itself. It'll figure it out on its own. So this code, Josh's code here, I want the machine learning algorithm to figure it out. Do you see that?
Yeah, no, that actually makes sense. Yeah.
And that's how it works. And actually what you're talking about is the old versus the new. The old pipeline before 2012. So you guys are truly living in different times, okay? Before 2012, the pipeline was Josh's exact pipeline. You have an image. Now, what I'm gonna call these filters. You would create all these filters. And then the filters would look at the image and would create versions of the image, multiple versions of it based on the different filters. So one filter would look at, you know, squiggly lines. Another one would look at lines that are in an X shape. Another one would look at lines that are, you know, thick versus thin ones. And it would create all of these things. These would become the features. And then you would still have the labels, right? And then you'd build your classifier. Do you see that?
Mm-hmm.
But you had to engineer these filters. It would take years of experts to come up with these filters. Nowadays, because now it turns out that these filters are nothing more than functions. You know, functions that take an input, transform it into an output. If you look, that's all I did, right? I took this image, call it A, and I made it into B, and this one into C, and this one into D, this one into E. So I basically just transformed that by running a filter. As it turns out, now with deep neural networks, deep neural networks are function approximators. So what that means is that you can really just lay out the architecture of filters, but the difference is here you have to write all this code. Here you leave this blank. And because you have the labels, the algorithm will learn what? Will learn that it'll create all these filters kind of randomly, but it'll learn that this one doesn't work, this one doesn't work, but this one works. And so the algorithm starts to then fill in this data because it starts to fill in the filters that transform A into C. Because why does it choose C and not the other ones? Because you have the labels. And you know that whenever you use the filter that gives you the C transformation, you get better results than with the other ones. Does that make sense, guys?
Yeah.
Yeah, and that's the CNN. That's why there's, whenever you talk about machine learning, you're always hearing about convolutional neural networks because they went with your old approach, which you proposed, to the new one where the algorithm fits it in. And now all you have to do is feed it the image. Some people still do feature engineering. I'm not saying you shouldn't, but I'm saying that now it's gone more in that direction. Okay?
Cool.
Any questions, guys?
Yeah, so like I mean this is kind of like taking it back a little bit.
Yeah.
But like so I mean yeah, on this slide, right? Let's say like you stringified all those images together to make one really long image, and then each pixel was a feature. Is that
Pixels,
like
yes.
is that actually like how that would be done? Is that like you would have like, like probably like tens of thousands of features?
Yeah, I see where you're going with this. You're going with the size of this. So let's say that the image I had said is 50 by 50, right? So that means that now the images are 50 by 250?
Yeah.
Right. And so how many features is this? That's your question.
I mean it'd be a lot.
It's 50 by 250. Right? So what is that? Let me get my calculator here. Unless anyone can do this in their heads. 50 by 250. 12,500?
Yeah.
Yeah.
So
That's why it's called big data.
Yeah. And then if you were to try to plot these, you would need to go to like the 12,500th dimension to like.
That's right. I like where you're going with this. This is our 12,500. Very good. That's correct. That's a big vector space, isn't it?
That's yeah, that's kind of trippy.
Maybe extraterrestrial beings can visualize that. We can't.
I can't even
Yeah.
go past the
all we can do is visualize R3. However, the math, any operation to generate lines or calculate distances in R3 also holds here. That's the beauty of it. So you can still process this data. You just can't visualize it.
Right.
And that's why we will learn when we look at singular value decomposition how to compress R12,500 into R3. But the problem with that, or R2, the problem with that is we lose a lot of information because I always give this analogy. It's like looking at the shadow of the person. So if you look at a shadow, you kind of get the outline, right? But you don't get all the 3D details. Make sense?
Yeah.
That was a great question. So any other questions, guys? Now, as far as a computer handling this matrix, let's think. Let's say that we had 100,000 of these scans, and then we have a feature space of 12,500. Do you guys see that? And then these are zeros and ones. Actually, this matrix is not that big, to be honest. A 100,000 by 12,500 could possibly be handled by your laptops. Like if you have an 8 gig RAM laptop and you use TensorFlow, if you use like an inefficient program? No. But if you use TensorFlow and NumPy, I think this matrix is still not that big. Obviously, if this was 1,000,000 samples and this continues to rise, which is possible, these are high definition or something, what you need to do then is you need to downsample the images, right? So that means make them a little bit more blurry, hopefully retaining some of the information, but you lose information. That's the downside. So I think for cancer detection, actually, you probably want to keep all the details, I would imagine. Is this clear, guys? Any additional questions? Nope. All right. Sounds like there's no questions. Okay. So then the next step is, I think we're done with the problems. That was the last one. Yeah. All right. So now I wanted to go over that homework because I think that's such an important topic. So now the next thing I want to do is let's just open up our Jupyter notebooks. Okay. So we're going to open up the Jupyter notebook and we are going to move on into the KNN algorithm. So remember that the next homework assignment is to implement KNN. Right, so implement KNN. So I'm going to share this. All right, so you should be seeing my Jupyter notebook here. And this will be, I just want to save this as Numpy examples. Okay, so now, what am I talking about here? So let me actually go back to the Word doc, or sorry, the whiteboard. So in NumPy, we have, so you guys know this X and Y, right? We have this data, X and Y. And, you know, let's define some features, some dimensions. So F2, F3, F4, and then sample 1, sample 2, sample 3, sample 100. And then we also have the Y vector, X and Y. And then here we have, you know, 0, 1, 1, 0, 1, dot, 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 0. Okay, so that's our data. You know, we already talked about it quite a bit in the examples. Now we want to find an efficient way of representing this data in Python. So probably you would think I'm going to have some kind of a list, or I'm going to have a vectors in a dictionary or something like that. Well, as it turns out, Python has a library called Numpy, right, which you probably heard of, that allows you to store data exactly like that. So exactly as you would write it on our, you know, on a piece of paper, that we can store the data just like that. And then the beauty about that is it's much more efficient when we want to perform operations. Does this make sense, guys? So you will see me now start to define all these X and Y by using, we're gonna now write them in the code, okay? Questions about that? All right, sounds like there's no questions. Okay, so now I think we are ready to switch over to the to the Jupyter notebook. So let me do this. I'm gonna do import NumPy. Can you guys see this?
Yes.
Yeah. I don't know how to zoom in on here.
I think it's the size is fine.
The size is fine. Okay. All right. So import NumPy as NP, right? So that's just an example. So now I want to do, let's say some variable, And I'm going to take a list of numbers, which we know how that should work, right? So I'm going to take 4, comma 5, comma 2, comma 6, comma 8. Just some numbers. And this would just be a standard Python list, right? But a Python list is not very efficient. I mean, it's efficient for a lot of tasks, but not for what we want to do. For what we want to do, we want to represent this almost like in the C code, so that it runs in the C code, and we can perform some vector and matrix operations, which are, you know, it's basically algebra, but on vectors and matrices. And we really don't have to know all of linear algebra. There's only really just a few operations of concern. So that will be easy to pick up. So then what we do is we call NP, right, Numpy, and we can say NP array. So now we will take our list, which is native to the Python language, and we're going to convert it into a NumPy array, okay? And that's the terminology that you need to learn. So just that one, NumPy array. Whenever if you talk about a list, you're talking about one construct in Python. If you talk about a NumPy array, you're almost talking more like an array as in the sense of C, but also at the same time, it is a NumPy array. So it's a matrix basically. Oh, there it is. I thought it was strange that it's okay, so there it is. You see that, guys? It's pretty much the same thing, right? It's pretty much, I mean, it has the same values. So it's not like the values were transformed, but notice that the values are no longer separated by commas. Do you see that?
Yeah.
Guys, yeah. And this is technically a vector, okay? So this is a vector, okay? Now you have a vector like in the sense of how I was writing my vectors a second ago. So just take a look at this. Maybe set up your Jupyter or just analyze this for a sec. All right, so what I'm gonna do today is I'm just gonna do some of these examples. I definitely think I will provide a link. It's already in my GitHub, so I will provide a link for you guys. Actually, I can do that. I'll do that at the end of class, so I don't waste time now. It's not homework, but I will strongly recommend that you go through all the examples. Okay, and try to. So it'll give you a lot of intuition about these matrices. And in particular, what's important about this is that as we start to write our code, I could have just left this out, right? And then we would have to write every single algorithm with for loops and everything, and you would have gotten the intuition of it. And I will usually try to give you the intuition with for loops and everything. But I actually think it's a good exercise that we try to write all of our algorithms, with NumPy, because if we do that, we are writing closer to how you do it in real life. You know what I mean? Like if you really do this work, you're not going to do it inefficiently. You will do it in this approach. Make sense? So it should be a pretty good exercise. All right, stop me if you have any questions. Otherwise, let's just practice a few of these. So I've generated a vector here. I can also generate this to be of a very particular data type. So you can see I can do data type, and then I can say something like float 32. See that? So now if I go to kernel and I do restart clear output, okay, And then now I'm going, well, let's save, I guess. And then I'm going to hit run. You see that? It's the same, same vector, but now I made sure that the values are floats, which, you know, instead of just regular integers. All right, so let's try now a list of lists. So this one, I'll try a different one. So I'm going to make a list of lists. Okay, and this is going to be, so notice I'm going to have a list, and then within that list, I'm going to have other lists. So 1, 2, 3, right? And then the next one is going to be 4, 4, 5. And then the next one's going to be 6 and 2. 6, 2. Notice that the dimensions are not the same here. Now, whenever you're building a matrix, you know, the dimensions have to match. They have to be correct, right? So in this case, let's see what we can do. We can make this be a numpy array, so np.array. Right? And in the numpy array here now we have list of lists, right? So list of lists. Okay, and now we can print B. And you can see it basically just prints out that even though it's a numpy array, it's a numpy array of lists. And we have these 3 lists over here. However, the problem was, you know, you saw those dimensions. Now let's just make a tweak to it. I'm going to change it. So I'm going to go back here and I'm going to say this one is 2, 11. So notice that now the dimensions are appropriate. This is a 3, should be a 3 by 3 matrix. So I'm going to go ahead. I'm going to run it, and you see the effect. Did you guys see the difference?
Yeah.
Yeah. So if this is, so now if we think about this as X, this is sample 1, sample 2, sample 3, and it has features 1, 2, and 3. So the columns are the features, the rows are the samples. Okay, so exactly what we were doing before, but now we have a way to create it in your code. So for instance, you guys have to do the KNN algorithm, right? So I would suggest that you do a matrix of 100 rows by, let's say, 10 features, something like that, right? And then you're going to have a vector for the labels of 100 by 1. So now you have a way to create it, right? You can create the data now. Remember, this is the first row, second row, third row. So you'd have to have 100 rows, right? And then and the features, these have to be consistent. So if you have 3 here, you have to have 3 in every single one. And then once you do this, now you have your data done. And so now you have a way of representing your data. Any questions? No? Okay. Now let's say, so hopefully this made sense, because this is a pretty important component, let's say. Now let's look at other little things that we can do as well with NumPy. We can create a array, a NumPy array, so an np.zeros of zeros, basically. So I just want, I want to initialize some vector to be of size 10, and it's going to be all zeros. And by the way, I want the data type to be integer, so int. Okay, so now if I do print b, right, and I run it, I can see that I created my vector and it's of size 10, and it has, should be size 1, 2, 3, 4, 5, 6, 7, 10, and it's all zeros. Okay. All right, so let's do another one, a very similar one, but this time it's going to be a matrix. So I'm going to do np dot zeros. Oh, sorry, let's make ones instead. Ones. And because this is going to be a matrix, I'm going to do, it's going to be of size 4, 6. So it has 4 samples, 6 features. And I want the data type to be float. Float. All right, so now I'm going to print B. Print B. You see that? So I made a new matrix. This is the X matrix. It's got 4 samples, 6 columns. 6 columns. And they are float type. Now let's say that I want to initialize a matrix to have a specific value. So I can do np dot full. I want it to be of size 3 by 3. So 3, 3. And I want the value to be 42. Right? So that is basically what I want it to look like. So then I do B, print B, hit run, and you can see the matrix, the X matrix, is now three samples, 3 rows, and 3 columns, 3 features, and the value is 42 for all. Now you don't always want your values to be specific number or zeros or ones. Sometimes you might need your values to be a range, right? So in that case, let's create a vector np dot a range, and we're going to say that we want a range of values from 1 to 30 with step size 3. Okay, so let's go ahead and print that out. Okay, print B. You see that I created the range. It starts at 1, then plus 3 is 4, plus 3 is 7, and so on, all the way until 30 basically. Make sense?
Yeah.
All right, so let's do one. Let's do now the following. This one will be, if we want it, like decimals, we can do B NP. There's another, NP. There's another technique called, using another function called line space. We try line space. And then this one gives us a, we can go from 0 to 1, but we want 20 values in there, right? So we go from the range from 0 to 1. Basically, it represents almost scale data, right? 0 to 1, and then we want 20 of these. We can print it, print B. Print it. And you can see now we've got our numbers. We've got a vector. Should have 20 values, I think. Starts at 0 and it ends at 1. Now this is the one that you will probably need for your KNN. Although this would be good just that when you're starting to get the code, where you're starting to get it to run, you can just create a matrix that is all random values. However, eventually, random data will have no patterns, right? We learned that in the cryptography class. So what that means, and machine learning is all about patterns. So therefore, you will need to change the data to be something a little bit more realistic. But here, at least, I can give you an example of how to create random data. So I can say numpy random dot random, and then I can specify the size, for instance, of the matrix that I want. So I want this to be a 4 by 4, let's say. So that means 4 rows and 4 columns. Okay. So then I'm going to do print B. Okay. And now that I have this, I can run the code and look, I've got some data there. It's randomly generated data. It's scaled data, which is what the data should look like anyway. And so it's good. This means I have 4 samples and I have 4 features. Now let's say that you're going to do, for your KNN problem, you're going to start with a random number, and that would be, let's say, 100, random numbers, and you'd have 100 samples, and you would have, for whatever reason, 9 features. Okay, that's your problem. So let's go ahead and run that, and you can see, although it doesn't look that great, but let me make it smaller. Yeah, that looks better. So you can see here, I got my X matrix there. It's got 100 samples, and all my data is there. Remember, each one of these vectors in the KNN algorithm, I would take this whole vector, right? This whole vector, and I would calculate the Euclidean distance, let's say, between that one and this whole vector. So it's always a calculation between the 2 vectors. Right? And that's what we did. When was it? On Tuesday, I think. We went over the Euclidean distance function, and I gave you the intuition of it, right? Remember, every row, the row that's highlighted, is a point in the vector space of R5, right? Because this is, has 5 features, so it's R5. So we can take the distance between any 2 points, and then that value is what we will need for KNN to get some of the intuition of KNN. Basically. Is this clear so far? Any questions?
So for the KNN, I'm just making sure, are we implementing the entire algorithm, or are we just doing this part of it?
You're going to implement the entire algorithm. So what I'm doing right now is showing you, for instance, efficiently how to create the data with Numpy, right? And then today, I'm just going to continue doing exercises like this. On Monday, so hopefully you'll have now a little bit more background on this. I'm going to give you the link so that you can finish up all the exercises. And then on Monday, I will go over the algorithm.
Okay.
More detail, but I'm not going to finish it. I'm going to give it to you like Lego pieces, right? And then you guys have to put it together. Okay?
Okay. Yeah, no, thanks.
But what I'm saying here, my point is that this code is important because this is your X matrix right here. So you will have to start B. So I should have named it X. You see that? That is your X matrix. Just like what we were doing in the first hour of today when we were solving the problems. But now this is that's your X data. And actually, when you do things in Numpy, it just makes your code where you would have spent, a lot of lines of code and for loops and everything. This just makes coding shorter, and it makes it more easier to understand. Once you pick up these little ideas of the vectors and matrices. Okay. All right. Good question. Any other questions? No? All right, so we talked about that one. Let's now do the same. So I'm gonna go, I'm definitely gonna do a smaller one. So I'm gonna copy this. This one's too big. So let's go down here. Now I'm gonna say, I wanna build random data, but this time I want the random data to follow a particular distribution. Okay, so if you guys remember, the reason why you take your statistics class, right, is that you want to understand about the mean, the standard deviation, and those things. So here, I'm going to create a data set with a mean of 0 and standard deviation of 1. Okay, so the way to do that is, so that means that the data follows a particular pattern. So it's going to be X, fine, np.random normal. It's a normal distribution. If you remember, normal distribution, just to remind you, looks like this, right? Anyone remember what it looks like?
Isn't it kind of bell-shaped?
A bell shape. Very good. Excellent. Excellent. So it's the bell shape, right? So it looks like that. So all your data follow this mean with some standard deviation over here. And that's all it is. So it's 0. So this is 0, and this is -1 and 1. And so all your values that we're going to generate them randomly are going to fall within here. So the majority will be around here, but there will be some outliers around here, and they're going to be within those values. Exactly. Very good. So that's exactly what we're doing. I mean, pretty simple. And so now let's make this a little bit. So we want this to be normal. We already said that. We want it to be, we want the mean to be 0, so we can say that. Then we want the standard deviation to be 1. We specify that there. And then let's make the matrix certainly smaller. So we're going to make it 4 by 5, right? 4 by 5, 4 samples, 5 columns, or sorry, 4 samples, 5 features. Okay, so we can go ahead and run it. And there we go. That's your data. You have 4 samples, 5 features. You have a data set that follows the standard. Now it follows a normal distribution. There's something in machine learning that is sometimes useful. It's called the identity matrix. So we're going to take a look at that. Sometimes we might look at that later. Now, don't worry about its meaning. Just worry about, creating these, understanding basically how you create things with Numpy. So we can do np.I, and that just stands for the identity. And then we're going to say the identity is a square matrix, which basically means it's n by n. So in this case, we're going to say it's 5. So we only need to specify 1 dimension. And then we're going to print B. All right, so now if I do this one, you'll see there's the matrix. What's important about it is that in the matrix, the diagonal is all 1s and everything else is a 0. So it's a useful operation sometimes to be able to do. You usually multiply this one by another matrix, and then the fact that only the diagonals are 1 allows you to extract certain type of data. So we'll see this a little bit later. It's equivalent to, sometimes it's almost like, you can think of it intuitively as taking a number 5 times 1. It's something analogous to that. So, but don't worry about it for now. All right, let's see now, what else can we do? So sometimes it's good to get information. Sometimes it's good to get information. So let me So you know what I'm gonna do actually? I'm gonna just explain all these problems instead of just letting you guys kind of do them on your own. So I'm gonna finish, I'm gonna continue doing these until the end of class today, and then on Monday, I'll continue with these. I think actually now that I look at them, I think there's value in me going over them, so I'll do that. And then I do still think that we should be able to finish KNN because once we have this background, understanding the KNN algorithm should be a lot more straightforward. So it'll save us time on the KNN algorithm, I think. So that's what I'll do. So I'll just keep working on these today and Monday, and hopefully I'll be able to get all of these done in 2 days. All right, so we did the identity matrix. So now let's look at another example. It's just, I honestly cannot emphasize how important it is for a major, for somebody interested in applied data science to understand Numpy really well. So this code just elevates what you can do significantly. All right, so let's go ahead and create a couple of matrices now. I'm going to create B1, and for now they're just going to be random, just so I can show some of the operations. This one is going to be a rand int. All right, so rand int, and let's say I just want it to be it's going to be one, two, three, four, five, 6. So the values are going to be random numbers from 1 to 20, basically. And then we can specify the size to be, let's say 3 by 4, 3 comma 4. So let's do that. All right, so now if I print B1, let's call this one B2 actually. Print B2. All right, so I have, as you can see, the values are, it is a 3 by 4. So it's 3 by 4. It is 3 by 4, and the values are from 0 to 20. Okay, good. So they're random integer numbers. Now let's do B3, and B3 will be the same thing, numpy dot random int, and this is going to be 20. And then now the size of this one, this will be a more complex one because it's going to be a cube, although you'll see what it looks like in, so it's going to be, instead of 2 dimensions, it's 3 dimensions. So size is 2 comma 4 comma 6. See that? And I need to add another parenthesis. So now I'm going to print B3. I run it. Oh, there we go. Do you see that, guys? Do you understand the intuition? So it's like we have 2 matrices. We have two-dimensional matrices, right? So you can see we have, this is 4 by 6, this is 4 by 6, but we have 2 of them. So this is the first one. This is the second one. So that's the 2 dimensions. Then the next dimension is the number of rows here, 1, 2, 3, 4, right? And then the next one is the 6, 1, 2, 3, 4, 5, 6. So it's kind of a cube type of a thing.
I do have a question. Can you process, so that's all one array, or is the space just there for convenience sake?
It's a matrix.
Okay, I'm sorry. I didn't realize there was an extra bracket at the beginning and the end. Never mind. Never mind on my question.
So this is something that, I do this sometimes, and it's, you have to really look at these brackets, exactly what you just said, right? And then you can see that here and here, right?
Yeah, like I said, I was just, that was a mistake on my end.
Get now?
Yeah.
So there's two-dimensional matrices, right? 1 and 2, and then each one has 4 by 6. So this allows us to create more complex data. Now, I will try to minimize these kinds of things because it really does take a lot of practice to get to them, right? So it's something that, it takes a little bit. Eventually, you get used to some of the tricks, but for the most part, I'll try to keep things simple, but just be aware it is possible to create these more complex ones, okay? All right. Any other questions? Now, let's say, so I have these two matrices and I printed them, but now I want to know things about them, right? So I want to know, for instance, what are the dimensions of B2, right? So I want to know the dimensions of B2. So I'm going to say print B2 dimensions, right? So I want the dimensions of B2. So then I can say B2 dot n dims. Okay, so if I run that, I get that the dimension is 2. All right, and that should make sense, right? It's a two-dimensional matrix. So if I try the dimension of B3, B3 dims, you can see it is 3 because it's got these, each one of these is a dimension, right? So one dimension is like on the X, on the Y, and on the C axis, okay? Now let's say that I want the size of B2. So the size of B2 should be 3 by 4. So let's try that. I'm going to say B2 size, and then it's going to be B2 dot size. Okay, run that, and it's 12, 3 by 4. All right. And also you can try other ones, like you could do data type. Just really quickly, I guess I can do data type here. And that, and it's int 32. Okay. All right, so that gives us a little bit of ideas. Now, the next thing that we probably want to look at is what is called indexing, right? So indexing is slicing things out of a matrix. So this is indexing first, and then we're going to do slicing. And basically, we want to be able to get values, just like we get values from our arrays, we want to efficiently be able to get values from our matrices or vectors, right? So in this case, I'm going to create a vector. I'm going to call it NP array. Right, so I'm going to make a Numpy array, sorry, out of a list. So I'm going to create a list of values 1, 3, 2, 5, right? So I have that. And I also want this Numpy array to be a data type float 32. So it's float, Okay, so now, first of all, we can print the value. So I can do print of A. But then also, let's say that I want to get the first element. And then this is pretty easy. So print, let's say I want to print first element. So that's going to be A in square brackets 0. You guys see that? So let's just run that. And you can see I've got my NumPy array 1, 3, 2, 5 all float. And the first value is 1.0. If I want the third value, which would be the number 2 there, I will extract, I'm just going to copy this. I will extract A2. This is going to be the third element. And there it is. Actually, wait. Oh, this is wrong, right? So it should be 2. 2. Yeah, and then it gives me the number 2. So this element here. Okay. Now, there's another very handy thing. Sometimes what I may want is I want the last element, but I don't know the size of the vector, right? I don't know the size of the vector, but I want the last one. So I can just say last, comma, and then I'm going to do A. And then instead, I just use a negative. So when you do -1, it's like you're counting from the end to the front, right? So you can do -2, -3, and you're just getting the values from the end to the front. So here, if I run this one, see I can get 5, which is the last one, without having to worry about what's the size of the vector, what are the indices, etc. Here I can also do print, you know, second to last, right? So, you know, before the last one. And for that one, then it would be A, comma, -2. Like that. So now I can run that one as well. And I get before last is 2.0, which is true. And that's kind of how it works. So that's indexing. You can index positive from front to end, or you can index negative from end to front. Okay, so hopefully that. All right, okay, so I think this is a good stopping point. We'll finish up these examples on Monday, and then on Monday, I will also go over, hopefully by the end of Monday, we will be able to do the KNN algorithm. As you will see, it's actually not that long. This is already helpful to create the X data. We've started to manipulate some of these vectors and matrices, and we already have the Euclidean distance from Monday. So we're in shape to complete KNN. So my plan for next week is to hopefully finish up NumPy, finish up the KNN algorithm, and possibly start a second machine learning algorithm called naive Bayes. Okay, so we'll take a look at naive Bayes and how that one works. All right, so that's it for today. If you have any questions, let me know. Otherwise, just start working on KNN, start thinking about it. And then remember that homework will be due hopefully a week from today, okay? All right, have a good day.
You too.
Bye.